Welcome to This Explainer. Today, we are unpacking an absolute engineering marvel, a spacecraft that actually did the impossible. It flew right into our star. For centuries, humanity has stared up at the sun, wondering about its intense heat and mysterious behavior. But staring from a distance just isn't cutting it anymore. Understanding our star is absolutely crucial for humanity's future. It's the key to predicting violent solar storms, the kind that could literally fry our electrical grids and wipe out our global satellite infrastructure overnight. So we're now living in this incredible era where we've sent a piece of human ingenuity right into the heart of the solar system to finally get those answers. Let's dive right in with a truly mind-bending number: 690,000 kilometers per hour. That is the blistering speed this probe hit while flying through an environment that would vaporize most metal instantly. To put that into perspective, at that speed, you could travel from New York to Tokyo in less than a minute. No way, right? The Parker Solar Probe didn't just casually drift toward the sun. It hurtled through its outer atmosphere, enduring conditions so violent they test the very limits of physics and engineering. And check out this extreme contrast. On one side, the front face of the probe is enduring a terrifying 1,400 degrees Celsius. On the other side, just a matter of inches away, highly sensitive scientific instruments are sitting comfortably near room temperature. It's like having a raging inferno right outside your window while you're chilling inside with the AC on. This perfectly illustrates how we got a probe closer to the sun than anything in human history without melting its vital core. It's an absolute masterpiece of thermodynamics, and it's the only reason this probe didn't just survive, but actively sent groundbreaking data back to Earth. Here is our flight path for today's explainer. Touching the sun, surviving the inferno, breaking speed records, discovering solar switchbacks, the coronal heating puzzle, and finally, the journey ahead. Section 1. Touching the sun, the impossible mission. So why take this massive, unprecedented risk with such an expensive piece of hardware? Well, the simple truth is, you just can't study a star's deepest secrets from afar. For decades, scientists have been observing the sun from observatories here on Earth or in low Earth orbit. But that data was fundamentally limited. We had to fly directly into the corona, the sun's incredibly chaotic outer atmosphere, because observing from Earth simply wasn't giving us the answers to how our star actually works. We needed to be in the room, so to speak, to measure the particles and magnetic fields exactly where the action is happening.
Section 2. Surviving the Inferno, the Heat Shield.
If you're going to fly into a star's atmosphere, your very first problem is, not melting into a puddle of liquid metal. Enter the TPS, or Thermal Protection System. This carbon composite shield is the unsung hero of the mission. It is the sole reason the probe didn't just survive the inferno, but actually managed to safely transmit data back to scientists. And here is the truly staggering detail. This miraculous shield is actually only 4.5 inches, or about 11.4 centimeters thick. Yet it handles front-face temperatures near 1,400 degrees Celsius. That's heat that would easily melt steel, all while leaving the delicate instruments tucked safely behind it at a cozy 30 degrees Celsius. It essentially acts as a high-tech shadow caster, allowing the probe to function perfectly in the most hostile environment imaginable. Section 3. Breaking speed records. The need for speed. Okay, so we have our armor, but how do we actually get there? You might think we just fired a rocket straight at the sun, but actually, it doesn't work that way. To fall into the sun, you actually have to lose the massive sideways momentum that Earth gave you when you launched. The Parker Solar Probe solves this by using Venus gravity assists in a really precise, carefully calculated sequence. By flying closely past Venus multiple times, the probe bleeds off orbital energy. This intentionally pulls the probe into a tighter and tighter spiral, eventually bringing it within just 4 million miles of the solar surface, whipping it around the star at those record-breaking speeds we talked about earlier. Section 4. Discovering solar switchbacks, solving solar mysteries. Now that we know how it survived the journey and the incredible speeds it used to get there, we can look at the unprecedented data it uncovered once it actually arrived in the corona. Almost immediately, the probe started detecting something incredibly strange, known as solar wind switchbacks. Basically, these are sudden, rapid reversals in the magnetic field of the solar wind. Imagine a stream of water flowing smoothly, and then suddenly it folds back on itself in an S shape before continuing on. This is a massive find. Understanding these switchbacks is absolutely crucial because this solar wind eventually washes over Earth, dictating space weather that can interfere with our GPS, disrupt communications, and even endanger astronauts. Before Parker, we had no idea these switchbacks were so common or so pronounced this close to the star. Section 5. The Coronal Heating Puzzle, the Unanswered Questions.
The switchbacks are really just the beginning, leading us to one of the biggest mysteries in astrophysics today: why the corona is so puzzlingly hot. I mean, it is incredibly hot, reaching millions of degrees, while the surface of the sun below it is actually much cooler. That completely defies common sense. It's kind of like walking away from a campfire and getting hotter. So there are three leading theories attempting to explain this extreme heat: nanoflares, which are tiny, continuous solar flares; magnetic reconnection, where magnetic field lines snap and realign explosively; and wave heating, where magnetic waves carry energy from the interior up to the atmosphere. What's absolutely fascinating here is the fierce scientific debate surrounding these very mechanisms.
Now, you might be wondering, why is none of this confirmed yet? Well, the truth is, it remains a genuinely open question because scientists are still actively analyzing the probe's fresh clues. This is real-time, cutting-edge science happening right now. The environment is so chaotic and complex that isolating the specific mechanism, whether it's nanoflares, magnetic reconnection, wave heating, or maybe a combination of all three, takes immense amounts of data. And the Parker Solar Probe is actively delivering that data today, actively changing the math and moving us closer to determining which, if any, of these theories hits the nail on the head.
Section 6. The journey ahead. What's next? The mission is far from over, and the stakes remain incredibly high. Right now, literally as you watch this explainer, the Parker Solar Probe is still out there. It's going to keep spiraling inward, utilizing more Venus flybys and getting even closer to the solar surface. It continues to fly through extreme heat and radiation, gathering data that will redefine our understanding of the star that literally powers all life and all technology on Earth. Every single pass through the corona brings a brand new treasure trove of information.
The sun still keeps secrets, but with the probe right inside them, what will we uncover next? We've achieved the impossible in aerospace engineering, surviving 1,400 degrees at 690,000 kilometers per hour. But the journey to fully understanding our star, that has really just begun. As Parker flies deeper into the corona, it promises to completely rewrite the textbooks. The question isn't just what we'll learn about our star, but what it will teach us about the billions of other stars in the cosmos. Thanks for joining me on this explainer, and keep your curiosity ignited.